This is a fairly challenging problem from our section on optimization. What we're trying to do is, with this particular radius of a circle, piece of paper, or something like that, what is the maximum possible volume that we could get for this cone if we cut a little triangle, sector out of this thing and fold it together as shown here. Our answer is going to be in terms of the radius of this thing. It's a daunting problem because the volume of a cone, which what we're trying to maximize, we're going to max this thing out, is 1/3 pi r squared over the area of the base, or the pi r squared is the area of the base. So it's 1/3 pi r squared times the height. And we don't have values for the radius of the cone once it's standing up, nor its height. So our volume is going to need to be in terms of this capital R, which is kind of a slant height of this cone, or the radius of the big piece of paper before it was folded into a cone. So what I did is I figured I'd just kind of drop a perpendicular down there and call that the height, and then this small lowercase r is the radius of the cone once it's formed. So we have this relationship, and I think once you see that relationship, you say, oh, okay, I can get the volume in terms of either little r or little h because of this Pythag relationship going on here. So we'd have h squared plus little r squared is equal to big R squared. Because little r squared is in our formula, it might be convenient just to get r squared isolated as big R squared minus h squared. And now we could use that as an expression substituted into this volume formula. So our volume formula would look like 1/3 pi, and now instead of using lowercase r squared, we'd use big R squared minus h squared times h. Now we could distribute this h in and then distribute the 1/3 pi in, and we would get a volume formula just strictly in terms of h, which is the thing that's changing, and this big R, which is a constant. So we'd get 1/3 pi big R squared h minus 1/3 pi h cubed. And again, I just got that by just kind of multiplying those three factors together. So that's nice because we've got the volume in terms of one thing that's changing, lowercase h. Remember, big R is a constant in this situation because the radius of the piece of paper is not changing. The radius of the cone will change depending on how big a sector you cut. So now, since we're trying to optimize or maximize this formula, we just need to take the derivative of it and set it equal to 0. So if we do that, we could look at v prime, which would be, and again, in terms of h, so this entire term right here, that factor, is the constant being multiplied by one factor of h. So the derivative of that first term would just be the constant, 1/3 pi r squared. The derivative of this term, the second term with respect to h, would be minus. The 3 would come down in front and make that 3 times 1/3, which is just 1 pi h squared. And if we just set that equal to 0, we'll find the value of h that will be the critical number for this, which will probably turn out to be our value of h that will maximize this volume. So solving this, we could just add this pi h squared over to the other side. So we're going to get pi h squared is equal to 1/3 of pi big R squared. We could divide both sides by pi, and we get h squared equals 1/3 of r squared. And from that, we get that h would be the square root of that, which is the square root of r squared, which we'll just say is big R, because we know it's a positive value, over the square root of 3, which is just going to be written that way. So that is our only critical number. Obviously, we'd have like h equals 0 as a domain, kind of the lower end of the domain. Chances are that's going to yield us a maximum volume. Now, I could verify that that's going to be a max using the second derivative test. So if I took the second derivative, I'd be looking at that expression for v prime right here and say, okay, what's the derivative of that? Well, remember this first term, because big R is a constant, that's all one big constant. So the derivative of that is 0. So we just need the derivative of this second term, negative pi h squared, in terms of h, which would be negative 2 pi h. And if you think about putting this value of h into here, we'd get v double prime at root of r over 3, or I'm sorry, r over root 3 is negative 2 pi r over root 3, and that's clearly going to be negative because r is positive and it's being multiplied by a negative, so that's going to be a negative value, which means our function has a zero slope at this value of h. It's going to have a zero slope there, and yet the second derivative is negative, which means it's concave down, so that means we're looking at a situation like that with a zero slope and being concave down, and that is a recipe for a max. So that is, this height right here is the height that's going to give us a maximum volume. But if you look at the question, it doesn't ask to say what are the dimensions. It just says what's the maximum volume. So all we have to do is use this value of h and plug it into our volume formula. So our volume formula is right here. So it looks like we're going to need to plug in h right there, and we're going to need to plug in h cubed here. So if we think of h as being good to go right there, h cubed would just be 1/3 r squared, which is what h squared is, multiplied by regular h, which is right here, which is r over root 3. So that would be big R cubed over 3 root 3. So there's a value for h cubed, and here's a value for h. So we can plug those two into our volume formula. I'm just going to call that star right there and see what we get. So our volume at the h value of big R over root 3 is, using this star formula from up here, it's 1/3 pi big R squared multiplied by regular h. Right there is regular h, and regular h is right here, so it is r over root 3. Now we're subtracting 1/3 of pi times h cubed, and h cubed is right here, so I can put in r cubed over 3 root 3. So let's see what we got. This first term would simplify to this guy over here is, let's see, in the numerator we're going to have a pi and a big R cubed, and in the denominator we have a 3 and a root 3. And we're subtracting, the numerator is again pi big R cubed, and our denominator is 3 times root 3, so that's 9 root 3. So we almost have a common denom to get our volume expressed as one fraction. We're just missing a factor of 3 in this first guy. So if we multiply him by 3 and 3, now our common denominator is 9 root 3. And you can see the numerator has 3 pi r cubed minus 1 pi r cubed, which leaves us with 2 pi r cubed. And that would be the maximum volume we can get in terms of the big radius of that paper that we were given in the original problem. So there you go. It's not maybe quite as tough as it would have looked from the outset.